6.3 solutions about ordinary points. Ordinary points. The first thing I have, this table here is set that we use it all the time. Those are the power series representation of the first functions you see in the first column of the table: 1 over 1 minus x, ex, sine x, cosine x, tan inverse x. And there are more to see, but the most important ones are these ones, ex, sine x, cosine x. Those are the ones that are used the most. We are going to look at what is an ordinary point, and if a point is not ordinary, what is it? What is it called? And then how do we get to the power series solution for differential equation, as we did last time. So first we consider the differential equation in standard form. This is the homogeneous differential equation: y double prime plus p of x y prime plus q of x equals 0. This is called the standard form of a homogeneous differential equation. We start by introducing a definition. A point x0 is said to be an ordinary point of a differential equation, the above differential equation, if both p of x and q of x are both analytic at x0. We use analytic a lot in complex numbers, so those who are going to measure in math, you're going to see it again in complex numbers. So one thing here I'm sure you forgot about is, what is analytic? You told us this last time, but I forgot. What is it? So analytic, p of x or q of x or both are said, so a function in general is said to be analytic if there exists, so this is there exists, a power series in x minus x0 with positive radius of convergence. It's not easy to come up with a function that is not analytic, but there exist functions out there that are not analytic. Here we usually, in this course, we don't focus a lot of non-analytic functions. You will see it again in complex numbers. Note, if the point is not ordinary, then it's called not analytic. It's called what? It's called singular. If the point is not ordinary, it's called singular. Those are just new terms. You want to get used to them. So let's look at this differential equation: y double prime plus sine x y prime plus exy equals 0. What are the ordinary points of this differential equation? So the first thing, we know that sine x converges for all x. This is like p of x. This is q of x. So p of x, which is sine x, converges everywhere for x, and q of x, which is ex, also converges for all x. The radius of convergence is infinity. If you scroll up back to the table, you will see it here. So sine x and ex, those two, they have radius of convergence infinity. You can find that out by taking this function, both of them, and use ratio test. That will give you the radius of convergence. So they converge everywhere. So this means every finite x is considered an ordinary point of this differential equation. Let's look at another example. xy double prime plus sine xy equals to 0. So is this written in standard form? No, it's not. So what we have to do is divide both sides by x to rewrite in a standard form. So what do we have? Recall, just to give you more information about this, recall the power series representation of sine x is x minus x cubed over 3 factorial plus x to the 5th 5 factorial. It's an odd function, so it takes the odd powers. And if I want to know about this, which is q of x in this case, we divide this series by x both sides. It will look like this. Then, to know where this converges, we rewrite this using sigma notation. If you want to know where this converges, this series we just obtained, which I did here, because we have alternating in the sign, so that's why I use -1 to the k, and then the denominators are odds, like this is 1 factorial, 3 factorial, 5 factorial. Any odd number can be written in the form 2k plus 1 and factorial, and the exponents are even, so 2k, and then you can use ratio test to find out it converges everywhere. So radius of convergence is infinite radius of convergence. So this means all finite x values are ordinary points. So in this section, we are mostly interested in x equals 0. X equals 0, like as a the x0, like x node equals 0. So basically, we say we find power series about x equals 0. Just to remind you about this from early of the previous section, if you reviewed that. So this is when the power series, always any power series about x0 is written in this form, the circle part. But when we say about x equals 0, this means this x node is 0. So then it turns out to become cn x to the n. Bounds are the same. So this is called a power series about x equals 0. So that's what we're going to focus on the most. So before we move forward with that, let's look at this one, this differential equation, y double prime plus natural log of x, y equals 0. So what do we know about this one? Recall the power series representation for natural log of x is the one you see on the screen. This one converges for all x from a little bit above 0 to exactly 2. So the question is, what happened at x equals 0? What happened at x equals 0? X equals 0, it's not the ordinary point, it's a singular point. The series does not converge at x equals 0. So that's why we call it singular point. Yes, diverges, you can say. The other thing, as another alternative way, which is easier than what we have been doing, what about if the differential equation is not in a standard form? Well, you can divide or rewrite it somehow to make it in, or to get it in a standard form. But you can still find out about ordinary point or not, or singular point, even if you don't rewrite it in a standard form. And how is that done? In this case, we come across what we call polynomial coefficients, not constant coefficients or something else. So consider the differential equation in this form: a2x y double prime a1x y prime plus a0x y equal to 0. If all these coefficients, called like say polynomial coefficients, they have no common factor beside 1, they have no common factor beside 1, then what happens? At x equals x0, this point is called ordinary if a2 of x0 is not 0. So what we call in polynomial is leading coefficient, but we can't call it leading here in differential equations. If a2 x0 is not 0, then it's ordinary, the point x equal x0 ordinary. If it's 0 at that point, or that in that one at a0, at a2, then it's called singular. So let's look at this example. X squared 4 y double prime plus 2xy prime plus 6y equals to 0. So what do we do here? If you take the x squared minus 4 equals to 0, First, notice they have no common factors beside the 1. If you take x squared minus 4 equals 0, you get x equals plus or minus 2. Since it's 0 at these points, then we have singular points at x equals 2 and x equals negative 2. If it's not equal to 0, then called ordinary points. So this means there's ordinary points almost everywhere except at x equals 2 and negative 2. How about another differential equation? I took the same one, I just changed x squared minus 4 into plus 4. Can x squared plus 4 equal to 0? Yes. You got x equals plus or minus 2i, imaginary. So you can still have singular points at the imaginary points or the imaginary numbers. That's okay. Now, the existence of a power series as a theorem. So a theorem I'm going to introduce here. If x equals x0 is an ordinary point of the differential equation. So first, you make sure you test or you somehow see that x equals x0 is really an ordinary point. For this homogeneous differential equation, a2x y double prime, a1x y prime, a0x y equals 0, we can always find two linearly independent solutions of the form of a power series. Y equals this, sum cn x minus x0 to the n. The solutions here for at least x minus x0 less than r is the radius of convergence, and here we can specifically here it represents the distance from x0, means from the ordinary point to the closest singular point, which could be real or complex. So all we are doing here is about x equals x0 equals 0. So you can say this would be n equals 0 to infinity cn x to the n. So let's look at finding a power series solution about x equals 0 for this differential equation. So how do we start about this? We know that x equals 0 is the ordinary point, right? Can you see that? This leading coefficient is 1. It's not 0. 1 is never 0. So now we are going to write y in the form of a power series around x equals 0, and we say it converges by the theorem at least x minus x0, but remember x0 is 0, less than, I put infinity because no singular points here, right? Because it says the r is the distance from the ordinary point to the closest singular point, but there's no singular point, so it's infinite. But that doesn't mean all of them work this way, so I wrote a note here. Sometimes there can be some singular points. So we're trying to solve this using get a solution to this in a form of a power series. So we have y, as we did in the previous section, y equals the sum cn xn. Then we need to find y prime and y double prime. So y prime, you find the derivative of this. Make sure the lower bound becomes 1 because 0 is not going to do anything. We find the derivative inside. And y double prime is what you see here. N starts at 2, it's not at 1 anymore, or at 0. And the next thing we're going to do is what we did in the previous section. Let me rewrite the differential equation again. Minus 2xy equals 0. Make sure that's the right one. Yes. Y double prime was the sum n equals 2 to infinity, n times n minus 1, cn x to the n minus 2 minus 2x, and y is the sum n equals 0 to infinity, cn xn equals 0. What are we going to do next? We can move the x inside. Sum is independent of x, it depends on the n's. N times n minus 1, cn xn minus 2, minus 2, the sum n equals 0 to infinity, cn x to the n plus 1. What do we have to do? As we did in the previous section, two things we need to match. What are they? Sub with k's, yes, we need to make sure the coefficients here, the exponents for x's are the same. So we assume k equals n minus 2 here. Assume k equals n plus 1. Solve for n. K plus 2, solve for n. K minus 1. Then the sum would go, instead of n, put k plus 2. K plus 2 minus 1, k plus 1. C sub k plus 2. X to the k minus 2, c sub k minus 1, x to the k equals 0, infinities. Let's see, if n is 0 here, if n is 0, then k is 1. If n is 0, k is what? If n is 2, k is 0. N is 2. So now the xk's match. We need to match the starting point of each one of them. The k equals 1 and k equals 0. We take the one with the lower bound with the smallest value or smaller value, which is k. So you can substitute k equals 0 here. If you put k 0, this will be 2 times 1 c sub 2 x to the 0 plus, now the c starts at 1. And everything else stays the same, k plus 1, c sub k plus 2, x to the k minus 2, sum k equals 1 to infinity, c sub k minus 1, x to the k equals to 0. So the one on the front is just 2c2, plus the sum stays the same, just copy paste everything here, k plus 2, k plus 1, c sub k plus 2, x to the k, minus 2, sum k equals 1 to infinity, c sub k minus 1, x to the k equals 0. Now since the bounds match, so I can rewrite all of this with k plus 2, k plus 1, c sub k plus 2, minus 2 c sub k minus 1, x to the k equals to 0. Now, in order for this to be identically equal to 0, this part must be 0, and this part must be 0. And then what we do here, we solve for the ck plus 2, which is 2ck minus 1 divided by k plus 2, k plus 1. What is k? K goes from 1, 2, 3, etc. Okay, so now we take k equals 1, and let's see what we get. K equals 1. That gives me c3 equals 2, c what? c0 over 3 times 2. Take k equals 2. What do we get? c4, 2c 1 over 4 times 3. Take k equals 3. c5 is 2c2 over 5 times 4. Right? But keep in mind, c2 in the upper right left corner here, it's 0. So just keep that in mind. K equals 4. We get c6, 2c sub 3, 6 times 5. But c sub 3, we found it. So you can replace that here, c square c0, or 2 square c0. 6 times 5 times 3 times 2. Getting everything in terms of c0 and c1. K equals 5. c7 equals 2c4 over 7 times 6. But c4, we found it. It's 2 squared times c1 over what? 7 times 6 times 4 times 3. And you can move on and on with this. K equals 6. c8 is 2c5 over 8 times 7. But c5 was 0, so this is going to go to 0. One last one, let's say c9, 2c6 over 9 times 8, which is c6 is 2 cubed, so 2 to the 3rd, c0 over 9 times 8 times 6 times 5 times 3 times 2. Now remember how we solved it in the previous section. c0 c1x plus c2x squared, c3x cubed, c4x to the 4th. c0 and c1, nothing changes. Those are the constants. c2 was 0, remember, 0x squared. c3 was 2c0 over 3 times 2. This was 2c1 over 4 times 3. And this can go on and on. Now we have, these have c0s and these have c1s. c0, 1 plus 2 over 3 times 2. I'm grouping the c0s together and the c1s together. Well, I should maybe add more terms. Let me add more terms here for each one of them. We got 2 over 3. I just put 2 terms, but we can show more terms. The next one was 2 squared over 6 times 5 times 3 times 2, x to the 6, 2 to the third, 9 times 8 times 6 times 5 times 3 times 2, x to the 9th, plus the next one is c1. It was x plus 2c0 or 2c1 over 4 times 3. Well, we took the c1 out. X to the 4th plus 2 squared over 7 times 6 times 4 times 3, x to the 7th plus da da da. You know, these are 2 linearly independent. Remember what it says here in the theorem. I'll come back to this. So first thing is, it's about an ordinary point. Find an ordinary point which was x0 for the homogeneous equation. We can always find 2 linearly independent solutions of this form. And that's what we just did. If you like, just for fun, to write down the solution in sigma notation. Let's see if we can do it for this one. Keep the 1 out there. Sum. Notice first they have 2, 2 to the 2nd, 2 to the 3rd. So we can assume it's 2 to the k if you want to take it out for all. And what goes inside? How can we come up with one like this? Now we're going to do something here over something, and x, all the x's, 3, 6, 9, the multiples of k. So what goes in the numerator? See, the denominators, there's like 3 times 2 times 1, then 6 times something something, then there's 9 times something. So what is missing? What is here? So we can rewrite it as 3k factorial, but let's see what's missing on the top. There's a 4 missing. So for the first one, nothing is missing, just a 1. For here, there is you need to multiply by 4, so there's a 4 there. And what is missing here for the next one? 7. What else? And 4. Keep in mind, k goes from 1 to infinity. I think came to 1. So to write this out, this is how we usually write it out. We write it out as 1 times, the first one was 1, then 4. I know there's a plus in there, ignore that for now. And then 4 times 7. So 1 times 4 times 7 times da 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 up to the 3k minus 2 that you guys suggested. So now test it out. If you take k equals 1, you will get just 1, and that's what I need. Plus, if you take k equals 2, you're going to get 6 minus 2, which is 4. If you take k equals 3, means you're doing the first 3 terms. That's what this means. You're taking the first 3 terms up to the 3k minus 2. So up to the 3k minus 2. So if you take k equals 3, you get 9 minus 2, 7. So you're going to take these numbers, you're multiplying 1 times 4 times 7, up to 7. So that's what I have here, 1 times 4 times 7. Make sense? plus C1. Keep the x out there. We're going to write the rest in a sigma notation. K equals 1 to infinity. We still have 2 to the k, as you guys can see. Now look at the denominators. 4 times 3, 7 times 6 times 4 times 3. You can write that as 3k plus 1 factorial. And usually what goes there goes up here. Now what goes inside the bracket or the parentheses? What is missing for the first one? We're missing here, we're missing 2. So you need to multiply by 2. We're missing here 2 and 5. So that would be 2 times 5 times, it goes up by 3. So times 8 all the way to the 3k minus 1. 3k minus 1. And if you like to know where the 3k minus 1 came from, think about it this way. The 2, 5, 8, this is an arithmetic sequence. If you remember, ak equals a1 plus k minus 1 times d. That's for arithmetic sequence. So a1 is 2, k minus 1, d is 3. So 2 plus 3k minus 3, you get 3k minus 1. That's where it came from. And same thing for the previous one, for the previous part. So is that okay? So now we say the two linearly independent solutions, we call them y1 and y2. So y1 of y1x is the first part, c0, 1 plus this sigma equals 1 to infinity, 2 to the k, 1 times 4 times 7 times times 3k minus 2 over 3k factorial x to the 3k. And y2 of x is c1 x plus the sum k equals 1 to infinity, 2 to the k, 2 times 5 times 8 times 3k minus 1, 3k plus 1 factorial x to the 3k plus 1. And those converge for x minus 0 or x less than infinity. Same as another example for the differential equation x squared plus 1 y double prime plus xy prime minus y equals 0, around x equals 0, as we did in the previous example. So we know here that if you set x squared plus 1 equals 0, you get x equals plus or minus I. Those are the singular points. Every other point is going to be ordinary point. So at x equals 0, we have an ordinary point here. So what do we do here? How do we start with this one? We start exactly the way we did with this one here. How did we start this one? If you scroll back up to the solutions, we started with the series x, cn x to the n. So we let y equal the sum n equals 0 to infinity, cn xn. From here you get y prime, which is n equals 1 to infinity, n cn xn minus 1. And then from here again you get y double prime, which is n times n minus 1 x to the n minus 2, and goes from 2 to infinity. Then what do we do next? We're going to substitute them in. X squared plus 1, y double prime is the sum, n times n minus 1, x to the n minus 2, and goes from 2 to infinity, plus x times y prime ncn xn minus 1 n equals 1 minus the sum n equals 0 to infinity cn xn equals to 0. Now we can multiply this out. We get n equals 2 to infinity n times n minus 1 x to the n plus the sum n times n minus 1 x to the n minus 2, n goes from 2 to infinity, multiply the x in ncn x to the n goes from 1 to infinity, and keep the last one the same. So notice all of them, they have x to the n, except the second term has x n minus 2 instead of x n has n minus 2. So how are we going to deal with this? So exactly as we did before, for this one, we take k equals n. For this one, k equals n minus 2. From here, n is k plus 2. Here, k equals n. Here, k equals n. And now we need to change everything. K equals 2 to infinity. K times k minus 1. X to the k. K equals 2. No, if n is 2, k equals 0. And we have infinity. Instead of n, we put k plus 2, then k plus 1, x to the k plus the sum, k equals 1 to infinity, k c sub k x to the k minus k equals 0, ck xk to infinity equals 0. So now they all have the same x to the k term. Now we need to get the bounds to start. So the largest one is k equals 2. So that one, we don't do anything for this. Keep it as is. For this one, we take k equals 0 when we get 2 times 1, which is 2, x to the 0 is 1, so that's a 2. And also we take k equals 1, that will give us 3 times 2 is 6, x plus, k equals 2 to infinity, and keep this the same. See, starting at k equals 2. Plus, here we take k equals 1, we get, wait a minute, did I forget something? I forgot something here. C sub n. C sub n. So there's a c sub n. We need to fill in all the missing terms now. C sub n. And here c sub n. Here c sub k. Here c sub k plus 2. And the rest are fine. So here c sub k, x to the k. And let me just fix this part. Fix this part here. 2 c sub 2 plus, when you take k equals 1, is going to be 6x c sub 3. So we take k equals 2, and now we finish with the first one, the second one, the third one. K equals 1, you get c1 x plus k equals 2 to infinity, k times c sub k x to the k minus c0 minus C1x minus k equals 2 to infinity, c sub k x to the k equals to 0. Now I'm going to group the terms that we need. 2c2 plus 6c3x. c1x cancels this, minus c0 plus the sum. K goes from 2 to infinity. First one was k times k minus 1 ck plus k plus 2 k plus 1 plus k ck. There's a ck here. I always forget the ck's. One of them has to have c sub k plus 2. When k equals 1, so this one here, we took 0 and 1, so this should be k plus 2 down there. So this is k plus 2, kck, notice this cancels this. Less work for us to do. X sub k equals 0. Now in order for this to be 0, you have to have this part is 0, and k times k minus 1 ck plus k plus 1 k plus 2 c sub k plus 2 equals to 0. Now, in order for this to be 0, you can rewrite it like this, plus the constants. And in order for this one to be 0, this has to be 0 and this has to be 0. 6c3 0 and 2c2 minus c0 is 0. So c3 is 0. c3 has to be 0. And c2 has to be c0 divided by 2. Keep those in mind. And from here we can solve for c sub k plus 2, which is negative k times k minus 1 divided by k plus 1 times k plus 2. Something went wrong here. Okay, so I see what happens here. There is a k there. I cancel them, but there's a k and there's no k there. So we shouldn't have canceled them out. So for now, we can fix this by the first part on the left, everything is fine. But these two can be combined into the sum k ck minus ck, like that, x to the k. So you can take, this becomes x minus 1 ck x to the k. K goes from 2 to infinity. So I combine them as 1 to make it easier for us here. So you can put that inside the bracket now. So it's plus k minus 1 ck x to the k equals 0. Now these two can be combined into factor k minus 1 out and ck. That will keep a k plus 1 ck. So now what do we got here? We got not just this, but there's a k plus 1 here. So then this gives us negative k plus 1. That cancels out. So c sub k plus 2 equals 1 minus k over k plus 2. As soon as you get to this point, then you're almost done, because it's just a substitution for values for k. So k here goes 2, 3, 4, etc. So now I'm sure if you take k equals 2 here, what do we get? We get c sub 4 equals negative 1 over 4. There's a c term here. ck. C2. But C2 is C0 over 2. So it's a negative 1 over 2 squared times 2, C0. Take k equals 3. C5 is negative 2 over 5, C sub 3, which is C sub 3 is 0. K equals 4. So C sub 6 is negative 3 over 6, C4. But C4, we found it, there's a negative 1 over something. So negative, negative, that's a positive. 2 times 4 times 6, C sub 0. If you take k equals 5, we get C7, which is negative 4 over 7 C5, and that's a 0. Take k equals 6, C8 is negative 5 over 8 C6, negative 3 times 5 over 2 times 4 times 6 times 8 C0, negative 1 times 3 times 5, 2 to the 4th times 4 factorial here, C0. And if you like to take more, you're welcome to do so. C9 will end up to be multiple of C7, which was 0, so that's a 0 again. And da-da-da. Then y equals C0 plus C1x, C2x squared, C3x cubed, C4x to the 4th, all the way. Then C0, C1x, C1 was nothing, just arbitrary constant C1. C2 was C0 over 2. C3 was 0. C4 was 1 over 2 squared times 2. C0. And the next one we had 1 times 3 over 2 to the 3rd times 3 factorial, C0 x to the 5th. And this goes on and on. Now there's only C1 term, C1x term, so let's put it out. Take C0 out, that'll give us 1 plus 1 half x squared minus 1 over 2 squared times 2 x to the 4th plus 1 times 3 over 2 to the 3rd times 3 factorial x to the 5th plus da-da-da. So I expect you to get to this point on an exam. You know, even if you don't want to write the general solution as I did earlier, that's okay. You can get all the way to this point. So in this case, the solution C1, call it C1x, and y2 is C0 times 1 plus 1/2 x squared minus 1 over 2 squared times 2x to the 4th plus 1 times 3 over 2 to the 3rd times 3 factorial x to the 5th plus etc.